chapter 4, the fundamental theorem of calculus. The proof itself, once I do all the development and get to it, the proof itself is actually pretty short. But it's very dense. There's a lot going on. So instead of just spending 5 minutes showing you the proof, I'm going to spend most of the class motivating the proof and making sure you actually understand where it comes from, because it's a very surprising result and critical to understanding calculus. So my motivation starts with a simple area problem that we're going to try to solve by drawing rectangles, like we did last class, and getting Riemann sums. And we'll quickly see that the approach we used last class doesn't quite work, and then we'll figure out how to improve it. So I want to find the area under cosine from 0 to pi over 2. So something like that is what cosine looks like in the first quadrant. So if I chop this up into a few rectangles, in rectangles, the area equation that I would get from doing the Riemann sum would be something like this. And this is like all the ones we got last class. Delta x is the width, and then times all the heights. Well, the height here, and here, and here, and here, the heights of all these rectangles is the cosine function. So I'm going to be taking cosine of the first x and the second x and the third x and all those things. So it'll be cosine of delta x plus, then 2 rectangles out is 2 delta x. How's it delta x? Delta x is the width of one rectangle.
Oh, so that's what you're doing.
Yeah. And so everything I'm doing here is just like we set up the Riemann sum last time. But what we had before, the first time, this was just delta x, 2 delta x, and the second time it was delta x squared, and then cubed, and we did examples like that. So now I have this expression for area. Any other questions about this expression? Okay, so now why is this all of a sudden a lot harder than last time? You can't take out a delta x, which was a key step. Before I could take out that delta x, and then I had 1 plus 2 plus 3, or 1 squared plus 2 squared plus 3 squared that I can simplify. But here, I cannot take out a delta x. So my only recourse, maybe there's some trig identity, that I could use for sine and cosine and all that. But even if I could find an appropriate identity, it would get really messy really quickly. So this technique, at least just doing like we did last class, is not going to work. So I'm going to come up with another approach that ends up sort of proving the fundamental theorem of calculus just for this one graph. And then using that as a motivation, I'll do the general proof of the fundamental theorem of calculus. But before I do that, I want to remind you of a couple pieces of background information just involving this sum. So the first thing to remember with a little star, I'm going to draw just sort of a little S-shaped graph like that, and chop it up into a couple rectangles. All right, so your graph doesn't have to be exactly like mine. It's just a conceptual picture. We had concepts on the very first day of this unit of a lower sum and an upper sum and a left sum and a right sum. Actually, I say that, and now I remember this is the class that was short, so we didn't do that example because of the pep rally or whatever, so we didn't do that. And it's okay that we didn't do that example. I'll just show this to you because it's a simple idea. We can draw these rectangles inside, and there's different ways I can draw them. I could draw something that's called a lower sum, where in each interval I draw my rectangle to be the smallest it can be inside that curve. So it takes the lower end of the curve. That's called a lower sum. If I add up the area of those 4 rectangles, is it going to be an under approximation or an over approximation to the real area? Under approximation. But as n goes to infinity and the number of rectangles increases, does it seem plausible that the area approaches the true area?
Yes.
Yes. And that's true. We're not going to prove that, but that's true. Okay. So a lower sum approaches the correct area. So this approaches the real area. Okay, an upper sum is just what you might think. Now all of these rectangles are the tallest they can be. So I take the tallest point in that interval and draw the rectangle. Over or under approximation? Does it still approach the true area? Yes. So lower also approaches the area. Then there's obvious other things you can do. You could pick the left end point for your rectangle. That would be a left end sum. Or you could pick the right end point for your rectangle. That would be a right end sum. And hopefully it's also obvious that all of those will approach the same area. So in fact, the height of my rectangle, it could be the tallest point, and that still works. It could be the smallest point, that still works. The left or the right. What about if I just picked any arbitrary point in that interval for the rectangle height? Any point that I wanted. Would the sum of the areas as n approaches infinity still converge to the true area? Yes. And you can sort of prove that using the squeeze theorem, because if the upper sum always approaches the area and the lower sum approaches the area, any point that I pick in the middle is going to be between the upper sum and the lower sum. So it all converges to the same area. So this is the fundamental idea here, that any point that I pick for the height, pick any point you want for the height, and it will still converge to the proper area. Converges to the same area. So for this rectangle, its height is right there. That's really going to be the key step in our proof of FTC, because I'm going to pick a point in the middle that allows me to simplify this big, complicated sum of rectangles. Because right now I can't do anything to simplify this. Questions there? Okay, so with this background idea, I'm going to set up the same computation over there, but I'm going to actually pick, say, 6 rectangles and be a little bit more detailed, and we'll see what happens. Positive ions, giving me power. Okay. So same picture, but I'm actually going to do 6 rectangles. And I'm going to add some notation to this. My x points I'm going to call xo, x1, x2, x3, just like we did before. So this is xo, x1, x2, x3, x4, x5, and x6. Those are all my endpoints. Now, since this is a cosine curve, what's the coordinate of any of these y values? Like if this is x2, what's the height right there? Cosine of x2, right? So I'll just write that for one point. I won't do all of them, but all those heights are cosines. And now I'm going to add another point. When we did Riemann sums last class, it turns out we were always doing a right endpoint sum. I was always picking, that's the right endpoint of the first rectangle, and the right endpoint of the second, and the right. I was always picking the right endpoints. Now I'm going to pick just some point in the middle. So I need to give that a new name. So we're going to introduce a new variable right here. It's some point in the middle. I don't know which point. I'm going to call that C. C1, C2, C3, C4, C5, and C6. So C sub I is in the ith rectangle, where I is between 1 and 6.
So they have to be the equidistant.
They are not the equidistant. In general, they're not the equidistant. It's just some point. Okay? So CI is somewhere in the ith rectangle. Ith. Yeah. Ith. And that CI will be where I find the height of the rectangle. Okay, so CI is where the height comes from. So F of CI is the height of the ith rectangle. And as an example, I'll draw, say, C4 over here. That's cosine of C4. So I guess instead of F, I'll actually write cosine. The same thing. So cosine of CI is the height of the ith rectangle.
Can it be bigger or smaller than?
It can be bigger. Well, it's got to be somewhere between the max and the min value, right? Because since it's in that rectangle, it's got to be in that bound. So now I'm going to find the area just like we've been doing. I just have a little bit more notation to go through. So the first thing is I'm not going to require all these xi's to be equidistant. So delta x isn't just delta x, right? It can change from problem to problem. So what would be the width of this first triangle that goes from a rectangle that goes from xo to x1? Exactly, x1 minus xo. So let's write our area. And it's going to be kind of long. It's the first width times the first height plus. That's the first rectangle that I just wrote down. The first width times the first height. Now you write down the second area to see if you understand what we're doing, and then I'll put it on the board. Should look like that. x2 minus x1 times f of c2, the second width times the second height. Any questions at all about that? And then does that same pattern just work for all of them? Yeah.
What if there's like 20?
That's what the dots are for.
Beautiful.
And my last one is x6 minus x5 times f of c6. Yeah.
And what you see for determining the width, right? You're only using x and x, so we're just using c for the height.
C has nothing to do with the width. It's some point on the inside. The height is f of c. Right. Other questions?
So why can't you just?
Go ahead.
So why can't you just use x1 or x2?
We can, okay, because what we saw last class, that will give us the area. So that will be a correct version of the area. But from what I see over there, if I just use x0, x1, x2, x3, I can't simplify that sum. So I don't know how to compute it. So the trick here is I'm going to show you how to pick these c's in such a way that this sum becomes very simple.
Wouldn't it just be more complicated with another variable?
You might think so, but it's not. It's not. Yeah, but Varun's exactly right. It seems like I just made this problem more complicated by introducing another variable. But it turns out that this variable is actually going to let every single term in this sum cancel out except the first one and the last one. And that will be super nice. Not exactly, but we'll see. We'll see. Andy.
Won't the x's always equal each other?
Won't they what?
Always equal each other?
No, because all of these heights are different. So the x's, right, so the distances here.
Yes, that distance won't equal x1 minus x.
Right, right. I mean, in general, it doesn't have to. It did in all those problems we did before. We made all the rectangles the same. But here, these widths are different, the heights are different, so there's no uniformity. Other questions? OK, so like I said, this c value is going to be instrumental to letting me simplify the problem. So let's figure out what c should be.
Are the c values like the midpoints of like?
They're not midpoints. There's some point in the interior,
Okay.
not necessarily the midpoint.
So then, like, why are you using those things?
Well, we'll see. We'll see. I mean, wouldn't it be nice if somehow, I mean, what would be a nice f of c1 to pick? I mean, it would be great if f of c1 happened to be 1 over x1 minus x0. Right? I mean, why would that be a nice height? That would just cancel out. And it would be awesome if f of c2 just happened to be 1 over x2 minus x1. Right? I mean, if I could pick the ci's so that this was true, then do we all agree that this would be really easy to solve?
Yeah.
Yeah? Well, I can't. But I can do something awfully close. And to figure out what that is, I want everybody to write down what the mean value theorem is from chapter 3. F prime of something equals something. F prime of c is f of b minus f of a over b minus a. Okay? Okay, well, how can I use that? Well, it's still not obvious, but I can manipulate this a little bit. Let's let a and b two of my endpoints. So let's just say f prime of c is f of x1 minus f of x0 divided by x1 minus x0. Okay, so I just let a and b be the endpoints in my first rectangle. Now, if I could somehow plug this thing in for f of c1, then what would happen? x1 minus x0 would cancel. But I can't. Why does this not just directly plug in for that?
Because that's the derivative.
Because that's the derivative. Well, why don't I can't plug that in because it's the derivative, right? So this is cosine. Why don't I take the antiderivative? What's the antiderivative of cosine? Sine. So if I take the antiderivative, f of c So cosine of C1 is going to be the sine of x1 minus the sine of x0 over x1 minus x0. Now verify that this is just MVT, but what did I pick for f? What's my f function? Sine. F is sine. So I applied MVT not to cosine. I bumped it up, antiderivative. I applied MVT to sine. Well, can I? Is cosine of C1, that's the same as f of C1? Right, because cosine is my function. So I can plug that right in. Now, but before I do, I want to make sure everybody is okay with this being MVT. Andy?
If you took the derivative, then why is the bottom still the same?
I'm not taking the derivative, okay? I'm letting f be the sine, right? Just say f is the sine and then write down what MVT says. It says this, that f of x minus f of x over x1 minus x0 is f prime is cosine. So I didn't take the derivative of both sides. Good question. Other questions? Okay, well then let's plug this in. So the area is x1 minus x0 times cosine of C1, right? Because that f of C1, I could write it, I should have maybe written it as cosine. It's cosine of C1, but we know that cosine of C1 is sine x1 minus sine x0 divided by x1 minus x0. And you see that it cancels out. It cancels out. And can I do the same trick for every rectangle? Yes, and they all cancel out. So x2 minus x1 times sine of x2 minus sine of x1 over x2 minus x1 cancels out, and on and on. Now I can simplify, and it gets even simpler. So those cancel out. I get sine of x1 minus sine of x0 plus sine of x2 minus sine of x1 plus sine of x3 minus sine of x2. What's happening here? They're all canceling out except for sine of x0, which is the first, and the last. Because way over here, I'm going to have a sine of x6, and nobody cancels it. So this whole area of these 6 rectangles is sine of x6 minus sine of x0. But what were x6 and x0? Are those just arbitrary points? And what endpoints did I pick for my original problem? 0 and pi over 2. They are my endpoints. So it's sine of pi over 2 minus sine of 0. If you took AB last year, now you see that this is just the definite integral of cosine from 0 to pi over 2. Yeah, it's beautiful. It's an absolutely beautiful proof. But I'm not quite done. There's one other detail I have to take care of. But before I do that, let's take a minute to take this all in. So I had a sum. I used MVT, not on the original function, on its antiderivative. And when I plugged in the MVT for the antiderivative, everything cancels out except the antiderivative of the first and last points. Now, I have not yet proven that the area under the curve is sine pi over 2 minus sine of 0. I have only proven that the area of those 6 rectangles is the sine of pi over 2 minus the sine of 0. So how do I go from 6 rectangles to the true area? Add more rectangles, and more and more.
So instead of sine x 6, it would be sine x to the n.
I'll add infinitely many rectangles, right? So I'll take a limit as n goes to infinity. This will approach the real area, right? But as n goes to infinity, how does this expression change?
It would be sine xn.
Sine of xn, but if I have 100 rectangles, what is xn for this problem? It's still pi over 2. If I have 1,000,000 rectangles, what's xn? Still pi over 2. So it's kind of tricky. It's an important step, but it doesn't really change anything. As n goes to infinity, that endpoint is still that endpoint. That 0 is still that 0. Infinitely many rectangles in the inside, they all still cancel out.
Because the middle ones change, but the last ones don't change.
The last ones don't change.
Wait, where's
So
the
there's no
sine
point.
biology?
There's no point about it.
Because so yeah, there's no point. What's sine of pi over 2?
1.
Thank you.
So if you made it instead of 6, if you went lower, if we had like only like 3 rectangles, it'd still be just that. Right? Even if you were down.
Yeah, even if you just did 1 rectangle, it would still be the same area. Yeah, so let me say that for everyone. Simmer made an interesting point. What I've shown here is that the real area is, quiet please, sine of pi over 2 is 1, sine of 0 is 0. So the real area here is 1, which is the area of 6 rectangles. But it works the other way. If I just drew 1 rectangle and I picked C this way, then the area of that 1 rectangle would be the area under the curve. So no matter how many rectangles I pick, if I use this approach, I get the true area. Turns out using just 1 rectangle is something called the mean value theorem for integrals, and we'll prove that next class. But basically, it should make sense that whatever this area is, I could basically flatten the curve out. I mean, there's some rectangle that has the same area as this shape, right? Some rectangle. So if you just did 1 rectangle, that would be, whatever that area is, just leveled out. Like a tank of water. It can slosh, but it's still a constant volume. Right. Questions?
How you got from that box to that box again?
This box to this box. This is the key step. Okay, this is MVT for anything, right? For any function in the world. My original function over here was cosine, so it would be nice if I could put cosine minus cosine over x1 minus x0, but if I did that, this would be sine. And so I can't make the substitution. So instead of letting f be cosine, I let f equal sine. And that's the clever insight into the proof. If I let f equal sine, then f prime, which is cosine, equals that thing.
So what if fx was y equals sine x? Would you change it to like this?
Exactly. What if f of x was sine x? That's the real question. So this technique that I did here for sine and cosine, is there anything about it that's particular to f being cosine? No, it would work for any. So if I let f be sine, then negative cosine, negative cosine. If f was tangent, secant squared, secant squared. If f was x squared, x cubed over 3 minus x cubed over 3.
Since it's cosine, is that supposed to be negative sine?
No.
Oh.
F prime. Right. Questions? Okay, what I want to do next and last is I'm going to give you the general proof of FTC. It's exactly the same idea. It's short. It's like 6 lines. Okay, but since it's general for any function f and for any number of rectangles, it's a little bit abstract. A lot of x's and i's and sigmas and things like that. So it may take you, a couple days to digest it all and figure out what it all means. But this is the idea behind the proof. Yeah.
How do you figure this out? Like, if you had no clue what this is, like, how do you just get from beyond sum to like
Insight and a lot of hard work. Okay, this is the proof of the fundamental theorem of calculus. The statement of FTC that I'm going to use is that the area under y equals f of x from a to b is equal to capital F of b minus capital F of a, where capital F is the antiderivative. So capital F has the property that f prime, big F prime, is little f. It's the antiderivative. So for over there, little f is cosine and big F is sine. So for the example we did, little f was cosine, big F was sine. Because it turns out, because of MVT, I can't just use cosine. I have to look at the antiderivative of cosine for the simplification to work. So that's the statement of the theorem, and now we're going to prove it. So first off, the area is a limit as n goes to infinity of a sum of the area of several rectangles. Right? That's what the area is. That's the Riemann sums we've done the last two classes. It's the limit and this is a very abstract way of writing what I already wrote on the board. It's the limit as n goes to infinity of the sum from I equals 1 to n of delta xi. Well, what's delta xi in words?
width?
The width of which rectangle?
A specific.
Of the I, yeah, rectangle number I. Right. So this is a width. What is f of ci in words?
The length.
The height or the length of which rectangle? Of rectangle number I, right? So in that problem on the board, I had XO, X1, X2, X3. I had 6 rectangles, so everything was numbered. Here, by using sigma notation, I can abbreviate it, but it makes it one step more abstract, so it might be a little bit harder to see. But that's the area. I take 6 rectangles, and then I let 6 turn into 10, into 20, into a million, into infinity. That's the area. I think we can all agree on that. Well, I want to prove that this equals FB minus FA. So the first thing I'm going to do is write what delta x is. Delta x is the width of a certain rectangle, so it's like x2 minus x1, x3 minus x2, x10 minus x9. I can write that as x sub I minus x sub, what comes right before I?
I minus 1.
I minus 1. That's the width of the ith rectangle times the height, which is still f of ci. Okay. Now, what can I do with this? I'm going to pick ci. Because what is c right now? Ci is any point, right, in the ith rectangle. It's true for any point in that rectangle. Now I'm going to pick a very special point. It's the point that comes from MVT. So I'm going to pick CI this way. It's going to be the point where F prime, oh sorry, where F of CI is capital F. And this is the big MVT step. Little f of CI is capital F of B minus capital F of A over B minus A. Why does that little f turn into a capital F?
Because f is the derivative.
Exactly, because little f is the derivative of f prime. So you could write it f prime equals little f, which equals f, or I guess I could write it on this side. That might be a little cleaner. So I'm picking CI to be this MVT point, but it's MVT for capital F. Now, once I've done that, the algebra kind of takes care of itself. So I'm going to plug f of CI in right here. And do that mentally. Do you see that cancellation is still going to occur? Top to bottom. So the area still is the limit, as n goes to infinity, of the sum of capital F of xi minus capital F xi minus 1 over xi minus xi minus 1 times xi minus xi minus 1. I equals 1 to n. If you ever wondered how many letters you could put in one statement, that's Varun.
It's because you're finding the integral of that function. What happens to plus c?
You're not, okay, you're not finding the plus, you're finding the antiderivative. It's a little change of definition. The antiderivative of cosine is sine. The integral of cosine x dx is sine plus c. So a slight change in definitions. Good question.
I have a question.
Yeah.
How did you get to the bottom of the
Oh, I see.
I just plugged this in there. So how I got from there to there is I just replaced f of CI with this MVT quotient. Sloaney. Because these are the two endpoints. This is the width. This is like B minus A. The two endpoints of your rectangle, A and B.
Why does it cancel with the I minus I minus 1 above that?
Because these are inside functions. Right? That xi doesn't cancel that xi.
No, I'm asking.
No, that one is going to cancel that one. It is going to cancel. Yeah, I just haven't written it yet. Right. Yeah, yeah. So it does cancel. So the limit as n goes to infinity of the sum from I equals 1 to n, f of xi minus f of xi minus 1, and the other terms cancel. And this was like over there, sine of x1 minus sine of x0, x2 minus x1, x3 minus x2. What happens to all the inside terms? So once they cancel out, which two terms are left? What's the smallest one I have? X sub what? X0 is my smallest term. So it's the one that's negative. And what's the biggest term that I have? Well, I goes from 1 to n. xn, and then because the n minus 1 term is going to get canceled. Well, actually, technically, it's still a limit. Okay, I left off the limit. It's still a limit. But now, what is x of n for this problem if I'm integrating from a to b?
B.
X of n is b. What's xo? A. As I take the limit as n goes to infinity, do a and b change? No, the endpoints are still the endpoints.
Wait, why can't you change the x the I minus f of x I minus 1 to f of the n minus c?
I'm not changing it. I'm taking this sum and all the middle terms canceled out.
Oh.
Right, all we were left with, like over there, was x6 and x0. The last term and the first term. All the other inside terms canceled out. Yep, this is called a telescoping sum. A telescoping sum means that all those middle terms canceled out. That's the proof. F of b minus f of a. So what this justifies, one example, and then the bell's going to ring. Yeah, so basically your test, the FRQ is going to be to do this proof. Yeah, the general proof. Okay, example. So now,
Let's do it with that.
yep, so now that the fundamental theorem of calculus is proven, we're justified in doing what some of you were doing in AB last year, is that the area under cosine from 0 to pi over 2, there's a notation for that. It's an integral sign with my two endpoints. And what this means is I find the antiderivative of cosine, which is sine, and I plug in the two endpoints. And a little notation for that that's completely standard is just a bar or a bracket with 0 and x over 2. And that just means you plug in b and you plug in a and subtract.
All that went into that. That's what we did last year.
All of that was the proof that says now this works. So you can find the area under any curve by taking the antiderivative. There are some homework problems in the book. I'll put those online because I don't have them in front of me. Yeah, on the homework calendar. Yeah, on the homework calendar. Thanks, everybody. Yeah, come on up, Andy.